Question 3. Compounds P, Q, and R have all been found in the atmosphere of one Saturn's moons. Okay, we can see this one is a triple bond, the cyanide. Okay, in fact, this is an alkyne. Alkenes, you know there is a double bond here. Alkynes, it's a triple bond between the carbons. Then we can have something here and then also this other side. Now here we have a cyanide. And also here, a cyanide. Okay, that's what we are seeing here. All right. Then Q is here, R is there. So they are saying that the equation for the complete combustion of P, okay, is shown. This is the one here. It is an exothermic reaction because the DH is a negative. Roman 1, the enthalpy change of formation of carbon dioxide is this one. Calculate the enthalpy change of formation of P. So what I'm going to do is to use the Hess's diagram. So first of all, the reaction I'm having here is C4N2, which is a liquid, then plus 4 oxygens, gases, then we get 4 carbon dioxide, and then plus nitrogen here. So these are our reactants, and then the products are here. But for enthalpies of formation, we are looking at 1 mole of a compound which is being formed, okay, from its elements in their standard state. So here there is a carbon, there is also nitrogen. Nitrogen exists as a dimer. It's a gas, this one is solid. And then we also have oxygen because now we are forming carbon dioxide here. So, gas. Now, I'll point here, formation of this, and that is the one they want. So, DHF of P. Okay, then we have DHF of carbon dioxide here. I would have put an arrow here for the formation of nitrogen, but enthalpy formation of an element is always 0. Okay, the same with this one of oxygen. So, and since here we are forming 4 moles of carbon dioxide, that means the enthalpy formation of carbon dioxide, I will multiply it by 4. Okay, negative 384 here. And of course, here we have the DH. So, using Hess's law, the steps taken are not so important, but what we look at is the initial steps, the reactants, and then the products. So I can do like this. This is clockwise is equal to anti-clockwise. Okay, so I will have DHF, then plus the DH, then will give me the 4 times negative 384. So meaning DHF is going to be equal to 4 times negative 384 minus when this one crosses. Now DH is this one here. So minus, then minus 2036. Of course, this one is going to be a plus, right? So what do we get all together here? 4 into negative 384, then plus 2036. This one will give us 500. And it's a positive value, so plus 500. Okay. Then Roman 2, they are saying that one of the products of the complete combustion of P is nitrogen gas. Explain the lack of reactivity of nitrogen. Nitrogen has a triple bond, okay? It has a strong triple bond. Nitrogen has this triple bond. Remember, each nitrogen is in position 7. So it needs 3 electrons to have its full octet. So they share those 3 electrons. Each brings the 3, okay? Now, nitrogen is electronegative. Remember the atoms which we know that are electronegative: oxygen, nitrogen, and fluorine. Now, nitrogen is electronegative. If it is electronegative, that means both of them are going to be pulling the electrons towards themselves. So in doing so, the dipole here disappears, okay? The dipole disappears, so it is nonpolar. So we shall add and non-polar. Sometimes they put 1 mark, other times they put 2 marks. So this will be the 1 mark and then the other mark here. Part B, Q forms when HCN, hydrogen cyanide, reacts with ethine. Roman 1, ethine, hydrogen cyanide, and Q are all weak Bronsted-Lowry acids. Explain what is meant by the term Bronsted-Lowry acid. Of course, this is a proton donor, or that is weak. So as an acid, I would say this is a proton donor. This is a proton donor. But then when it comes to weak, that partially dissociates in solution or in water. That partially dissociates in solution, or you can say ionizes, okay, in solution. As simple as that. Here I would have talked about the weak, and then the proton donor is the acid. So don't say this is the acid that partially dissociates in solution. No, the proton donor. Then Roman 2, they are saying that ethine, hydrogen cyanide, and Q all contain triple bonds between the 2 atoms. A triple bond consists of 1 sigma bond and 2 pi bonds. Draw a label diagram to show the formation of a pi bond. Of course, for the pi bond, there is going to be what we call the sideway overlap of the p orbitals. Maybe this one is like this and another one is here. Then they bend. So they form, just like you can raise your hands up straight, okay? And then you bend them. And then also down this way. So they form the ball. That means the electron from this side and also this way, they can move around. So that means for that case, in such a molecule, there is going to be limited rotation, okay? So we are going to have what we actually do in books. We put this one here, the plane, where, of course, you are going to have one of the p orbitals. So we have something, let's say like this. This one here, and also this one here. So they bond. It is head-on overlap. They form the sigma bond. So for any double bond, you should know that there is a sigma bond, this one, and then a pi bond. There is a sideway overlap here. So there is always that sigma bond. So there is that overlap up and then below. So in books, it will be represented like this. Okay. So what we shall do here is to put this plane here, and then we put something like this here, and then something like this down here. Okay. So we shall say that a pi bond, a well-labeled diagram. So I will say this and this is a pi bond formation. So I will say this pi bond is made up by sideway overlap of p orbitals above and below the plane. So that is that. Then the next one, P and Q can be detected in the atmosphere by infrared spectroscopy. Okay, identify 2 absorptions and the bonds that correspond to these absorptions that will appear in the infrared spectra of both P and Q. Now, back then, they used to give students what we call the specimen data booklet. Okay, so but currently they give you everything needed. So that table, they put it in the paper there. You just go there and you look and then you tell. So when we look at P and Q, you can see that it has a triple bond between the carbon, okay? And it also has a triple bond here, the cyanide. And when we go to the other diagram, even Q, when we go to the table, we should look out for the triple bond here for the alkynes and also this one for the nitrile, okay? So let's go and check. So in the data booklet, this one here, we can check for those absorptions. The chemical shifts. This is A level content. Infrared is here. So we can see here, sorry, look at alkynes, this one here. The absorption is here, 2150, 2250, okay? So we shall just write here that we are going to have an absorption at, I will say absorption at 2150 to 2250 per centimeter for the carbon to carbon triple bond. Okay, then we must get another absorption at the range at what for the carbon to nitrogen triple bond. Let's check that one out. So carbon to nitrogen, nitrile is here. So it is 2200 to 2250. Okay. Currently, they give you this table, so you don't need to worry. So this one has to be 2200 to 2250. Okay, per centimeter. As simple as that. Then next part D. We are given R here, reaction 1, then we are seeing this one here. Now you can see that this is an alkene here, then it polymerizes, okay? That is addition polymerization. And what else? Dilute sulfuric acid, then heat under reflux, reaction 2. I think it is, this one is going to become, that is hydrolysis. So this one is going to become a carboxylic acid, okay? And then from here, what we are having here, it is a reduction. So they are adding hydrogen there. If it is hydrogen gas, then there has to be a catalyst like nickel, okay? Then this one will be reduced to an amine, and then this one here, the alkyl. Okay, now let's go. Name the type of reaction shown in reaction 1. Of course, that is addition polymerization. Polymerization. So what happens is that this one opens up like this, and also this one opens like this. Then this is how you form that. Okay. Next, draw the structure of S, the organic product of reaction 2. Remember, this is hydrolysis. Okay, acid hydrolysis of this one, it will become a carboxylic acid. So I will just write this one, but then here I put COOH, as simple as that. So we shall have C here, then C, then there is a hydrogen, then the hydrogen here, there's a hydrogen here, then here COOH. That is what we shall have there. Then name T. Which one is T? This is an amine. This one here is an amine. So we have, this one is a propyl group. So propyl amine. But this amine group can actually be on the second one here. Then it becomes 2-amino. So because there is that isomer, then I'm not going to say propyl amine. But I will say, I will mention the position of the amino group. So I will say 1, then amino, propane. Okay, why? Because if we have NH2 here, then this is CH3, then CH here, this will be 2-amino propane. Okay, all right. Then next, Roman 4, T can also be formed by the reaction of bromopropane with ammonia. Okay, state the necessary conditions for this reaction. There has to be ethanol. Okay, there has to be an ethanolic solution, as the solvent. Okay, so ammonia has to be applied under high pressure. has to be in excess under high pressure and temperature. Okay, high pressure and temperature. Okay, in a sealed container. In a sealed container. Now, why are we doing this? If we have this CH3 here, CH2, CH2, NH2, okay? This is the one that is from the primary amine. Now, if ammonia is not in excess, then this one is again going to attack. This one can still attack this one, okay? We have Br here. Let me write CH2, CH2, CH3. So remember, this one is partially negative, this one is partially positive, because this one is more electronegative, so it attracts bonding electrons towards itself. Then this one will attack this carbon here, which appears to have lost electrons, and it has the electrons available. Then this one will come off. Now we are going to have CH3, CH2, CH2. Then there is NH, then CH2, CH2, CH3. Okay, so it's positively charged, and then you give the electrons to the aluminium, to that nitrogen. So you have CH3, CH2, CH2, NH, then CH2, CH2, CH3. This one is a secondary amine. And this one can still attack this one again. Then you form a tertiary amine until when the hydrogens on this nitrogen are done. You see that? So ammonia has to be in excess to avoid this further reaction. Okay? It has to be in excess to avoid the production of secondary amines and then tertiary amines. So it is a mixture of all of those. So that's why they say you need these necessary conditions.